igneous rocks are the first of the three rocks that we're going to talk about. And we're going to talk about igneous rocks first because they're the first rocks that appear on the earth. Igneous is to ignite. They are fire and brimstone. They're volcanic. They are emerging from within the earth. So these are the rocks that are coming out of those convective cells from the asthenosphere. They are being pushed to the surface of the earth. They're being created internally. So they are endogenic. Like genesis is to create. Endo is internal. So internally generated. The igneous process is such that these rocks solidify into a solid state from either magma or lava. When it's magma, magma and lava are the same thing. Magma is the stuff when it's inside the earth. Magma or lava is when it emerges to the surface of the earth. All right. With that, then, we see that an internally produced igneous rock is going to have very different structure than an externally produced rock. So an internal rock is intruded. It's pushed into the inside of the earth between layers of rocks, similar to a diagram that we showed you. Extruded is pushed out of the rock. That's the lava. All right. The oldest rocks on our planet, those cratons and those shields, are igneous rocks. The Canadian shield is Canadian granite. And they are very classically configured very similarly to this particular rock here. Very speckled looking rocks. So with igneous rocks, whether they are intruded or extruded is going to determine how tough those rocks are, how much they can withstand weathering and erosion and therefore degrading. And that is dependent on how fast the rock cools. If the rock cools really fast, the crystals are going to be small. If the rock cools slowly, those crystals have time to grow into larger units. So it would be like asking, what is harder to lift and remove? A small shoe-sized box from your house or a box that's the size of a refrigerator, right? The same goes for rock size. It's very hard to erode and remove a large crystal as opposed to eroding and removing a small crystal. So it's easier to break down rocks with small crystals than large crystals consequently. Cooling then, and the rate of cooling, is really just a function of, did it cool outside the surface of the earth or inside the surface of the earth? If it cools on the outside of the surface of the earth, it's going to cool faster. So it's going to have smaller crystals, or what we call lattice, a smaller, finer lattice. If it's going to cool in the earth, such as in a batholith or a pluton, then it's going to have an opportunity to take a longer time to cool, which means it's going to have a larger crystalline structure or lattice structure. So with these two igneous rocks, we can really see or appreciate the difference between a very fine, tightly latticed rock structure and a very coarse, large latticed rock structure. And recognizing that, you can imagine, picking these little tiny flecks of rock out much easier than something that's much larger like this, right? This is going to take much more effort. The surface area has more super glue, so it's going to bind to the surface much more readily than something that has a smaller surface area to bind to. So that intrusive and extrusive, to give you an example of each, is an intrusive rock is going to come out from the center of the earth and maybe not make it to the surface. It's going to then maybe just produce a dome or a bubble, if you will, under the rock layers. Or you could get something like these lateral dikes underneath this volcano. So everything in here is underneath and inside the rock. So this would be all intrusive. This neck of this volcano and these lateral features, which are dikes, would be intrusive rocks. They would have a greater structural integrity, larger lattice structure, larger crystalline structure. Then, if the matter was expelled out the surface of the earth and then cooled on the outside here, it would cool much more rapidly on this extruded volcanic cone. Some examples of rock formations or volcanic rock formations, igneous rock formations that don't look typical are included here. So probably one of North America's most classic is Shiprock and its associated dikes. So I've got this dike here, which is the authentic version of this illustration right here. All right. So what we're looking at Shiprock, and I'll go back to that slide in a minute, is every one of these layers emerged at the surface of the earth, small crystalline structure, easy to erode. But at some point in the history of Shiprock, which was a volcano at one time, the magma pooled into the neck, into the conduit, and into the dikes, and then didn't erupt. It stayed in here and then cooled inside the volcano proper. As time passed, the volcano, which was out here and out here, eroded, left what's left of the neck behind. So this would have been the neck or part of the neck of the volcano. And here is one dike, and you can kind of see another dike here. And if you can kind of squint, you could see what used to be a nice continuous dike, but it's now eroding. All right. Not too far away from Shiprock, and Shiprock is in the northwest corner of New Mexico, is Sunset Crater. And Sunset Crater, like Shiprock, is on the Colorado Plateau. We don't often think of northern Arizona, northern New Mexico, southern California, or Colorado, wow, southern Colorado and southern Utah as being volcanic, but they have volcanic features there. And one of those other features here is Sunset Crater, which is tephra. Nice way to think about what tephra is like is it's like that hot patch that they patch the potholes with at the end of winter. It's warm, it's little chunks of stuff that when compacted stick together. All right, so it's kind of friable. It's got some movement if you put some foot pressure on it. But it looks like a volcano. It kind of is. It's definitely an extrusive feature that is volcanic in nature, but it emitted pyroclastics of a tiny circumference. This super cool stuff is volcanic tuff. It's like an ash that was deposited over many periods of time. So there were many volcanic eruptive ash events. And if you look in the background here, that feature should look kind of familiar, right? It's not Shiprock, but it's similar to Shiprock. So this was the neck of an ancient volcano, and it was this volcano that erupted all of this. Thinking about this is a nice little footpath, which is about 3 feet wide. That gives these bushes and trees probably an 8-foot height. So if I go 8 foot and then another 8 foot and then another 8 foot on top of that, we're looking at 20 to 25 feet of volcanic ash that deposited over time. It's got these really cool features because ash is soft. It is easy to pick up by the wind because it's small in grain. So over literally centuries, the wind has picked up and removed ash little bit by little bit over time. Couple of other intrusive features. Nearly all of Yosemite National Park is a huge batholith. And so what has happened with Yosemite is that prior to that gorgeous chain of mountains, the Sierra Nevadas, they were all of this plutonic intrusive feature here. So what happened is matter pushed in under the Earth's surface, it cooled here, and all of this overburden over time was eroded away, and then this was left behind, and this became the Sierra Nevadas. This became the mountain, and then a series of mountains, if you will, to be Sierra Nevada. So what we've got then is all of these, you can almost imagine them as just sort of bubbles of plumed material. This is Half Dome right here, that were cooled underneath the Earth's surface. Very, very tough rock. The Sweetgrass Hills of northern Montana are likewise an intrusive feature. And they look more like little volcanic cones because they're sort of conical in shape, but these are intrusive volcanic cones. And you don't think of Montana as being an area of volcanism either. Columnar joints are very common along areas where they are in conjunction with a body of water. So what happens here is the lava then interacts with a water body, and the nature of the water body cooling them off cools them into their crystalline lattice structure, and then cools them into these hexagonal shapes. And there are several of these around the world. The Black Beach in Iceland is exceptionally famous, but there are many columnar joints in Iceland. Probably more famous than the Black Beach of Iceland are the columnar joints of the Giant's Causeway in Ireland. Exfoliation domes are batholithic as well, and what happens here is that imagine a rock cooling just like the browning that we talked about before. Remember that the outside cools first, and then the inside cools a little bit more, and the next layer cools, and the next layer cools, and finally you've got a rock hard brick of a brownie. In this case, what happens is, and in all cases actually, when things cool, they contract. When they're warm, they expand. When they're cool, they contract. So this rock cools and contracts around the not yet cooled rock beneath, inside. And so that next layer cools and contracts, and then it cools and contracts, and you get these concentric layers, just like an onion. So when these exfoliation domes, these structures then erode, they erode one layer at a time. So Enchanted Rock is just outside of Austin, Texas. But and this is not Enchanted Rock, this is Yosemite, but you can see the nature of all of these little layers where you've got one sheet and then another sheet and all these tiny little layers. And what happens is, once you remove a layer, you take the pressure off of the layer beneath, and it's sort of, it's like it exhales. It just expands a little bit. It creates some cracking, loosens itself from the adjacent layer beneath it, and then that layer over time is free to erode. So these things come off in sheets almost. This is Crater Lake. This used to be Mount Mazama. And this volcano, you can see sort of, how broad the circumference is. And it was a massive volcano. Here you can see a plume, and here is Wizard Island. This is some magma which was coming up out of it. So this is the edge of the volcano. So we're looking this way on this photo. That's this way on this photo. This here that looks like the edge of a mountain range is this edge out here. So Mount Mazama, Crater Lake is a massive volcano. I want you to think about, how the heck did this water get in here? Because it would have to have flowed uphill, and that's not possible. So how did this water get here?